The objective for today is to finally define these trigonometric ratios you've seen before in relation to a right triangle and a specific reference angle. And then I also want you to be able to calculate missing angles or sides in a right triangle using these trig ratios. In g.srt. 5.2, we talked about two special right triangles, 45, 45, 90 being one of them, where we have these right isosceles triangles are always going to be similar because angle measures are preserved and sides are proportional. And so if you take a look at this one example here, it's listed the sides, generally speaking, as x and x, congruent because they're opposite congruent angles. And we were always able to write the hypotenuse as one of these legs times the square root of 2. Looking at these ratios then, we could always say that the ratio of the leg to hypotenuse was 1 over root 2, which simplifies to that decimal. We could also say that the ratio of a leg to a leg is 1. The sides are always congruent, so if you write the ratio, it'll always equal 1. True for all 45, 45, 90 triangles. But there are many more right triangles beyond the 45, 45, 90 and even the 30, 60, 90. And so we'll need some common language to begin looking at these triangles, introducing the term reference angle. And so if you look at the triangle on the left here, we have A as the reference angle. Drawn in the diagram, you'll see that opposite A is called the opposite leg. Adjacent to A that is not the hypotenuse is called the adjacent leg, and then the hypotenuse will always exist across from the right angle in these right triangles. Even if we switch it up and look at the reference angle C, you still have that the opposite leg is opposite angle C, so in this case it's the long leg. The leg adjacent is going to be the short leg BC because we cannot have our adjacent leg be the hypotenuse. The hypotenuse again is always going to be across from the right angle. So go ahead and take a moment, now you try some, resume the video when you're ready to compare. The side opposite angle A in this case is going to be segment BC. The hypotenuse across from the right angle is going to be segment AC. And the side adjacent to angle C is going to be not the hypotenuse but the segment CB. On this page in the notes, we're looking at the 30, 60, 90 triangle and writing ratios of the sides. And so if you look at this base triangle, we have x as the short leg, which means x root 3 is the long leg, and 2x is the hypotenuse. And if you look at these ratios, the opposite to hypotenuse is always a half. When you look at the opposite to adjacent, 1 over root 3 is always going to be that decimal, and then the adjacent to hypotenuse will be that decimal. That's in reference to angle 30. If we switch it up and look at the 60-degree angle as our reference angle, you'll notice that we still have a half, we still have the 0.866 decimal, and then the opposite to adjacent switches because we do reverse the order. But we're looking at similar sides, these fixed ratios, and so there are some commonalities in triangles, which leads us to trigonometry and triangle measures. Specifically, there will always be 3 fixed ratios of sides in regards to a reference angle and a right triangle, and then the opposite is true. If we know the ratio of 2 sides, then we know that exactly 1 reference angle is going to exist, and trigonometry is the most precise way for us to know that. At the bottom of the page are our 3 trigonometric ratios that, given 2 parts of a right triangle, allow us to solve for other parts of the triangle. You might have heard of the acronym SOHCAHTOA. And so if you notice, the S stands for sine. You're always please going to read that sine, even though when we set up formulas using it, it looks like sin, but you pronounce it sine. And then sine compares the ratio of opposite sides to hypotenuse in a right triangle. If you look at ca, that's cosine. It's written as cos when you're writing the formula, but it's pronounced cosine. You'll read it cosine. And that's the ratio of the adjacent to hypotenuse in a right triangle, so that's ca. And then toa is tangent, all right? And so you'll always read it tangent, but if you notice in the formula, it's written as tan. And then that's the ratio of the opposite side to adjacent. So sine and cosine will compare either leg to the hypotenuse, and then the tangent ratio is the one that compares the 2 legs to each other. Right here is my favorite part of trigonometry, where it lists the reference angles 1 through 90 degrees, and it shows you the ratios of sine, cosine, and tangent. No matter the side lengths, the ratios would always be the same, so these decimals are constant. And highlighted in the yellow, you'll notice perhaps the 30, 60, 90 triangle and the decimals that you saw on the previous page, or even the page before that, you might notice those 45, 45, 90 decimals. And so these values, folks, are ones that you're going to have to memorize. Just kidding, that's why you have your graphing calculator, so please have that handy. We're going to go through how to use that effectively. The first part of these notes references the chart from the previous page that you do not have to memorize. So we're going to skip down to the bottom 3 examples and talk through them so that you can try them on your own using your graphing calculator. Looking at the first example, we have a right triangle. If you notice, we have this symbol for the angle. It's called theta. And we need to figure out what trig function to use to solve for theta. Given theta as a reference angle, we have 13 as the side opposite, and we have 34 as the side adjacent, as it's not the hypotenuse. And so thinking of SOHCAHTOA, the one trig function that references the opposite and the adjacent is the tangent function. And so tangent of theta is equal to the ratio of the opposite side over the adjacent. And so this setup right here shows the plug-in of the information we know. And I've got to say I'm not a fan of the decimals that they have in the rest of their work. So what I would expect of you is to begin to understand that in order to get theta on its own, just like if we had 2x equals 4, we would divide both sides by 2. Here, if we want to get the theta alone, we're going to do what's called the arctangent or the inverse tangent to both sides. And so you'll notice that if I do the arctangent to tangent, I'm left with theta. And then on the right-hand side, I would also take the arctangent of, let's keep it as exact as possible, 13 over 34. Using what you saw on Friday, go ahead and enter this into your calculator. And that's how we get theta equals 20.92 degrees. Be sure to label it with degrees, please. And so taking a look at the next example, we have theta again. We have 2 sides of the triangle. If you notice, theta is our reference angle. We have the hypotenuse, which is opposite the right angle, and we have the side adjacent, as it's not the side opposite. And so again, looking at SOHCAHTOA, the trig ratio that compares the adjacent side to the hypotenuse is cosine. And so cosine of theta equals the adjacent 25 over 32. And again, you're starting to practice that the inverse cosine or inverse trig function of any function is going to get the theta on its own. And then what you do to one side, you do to the other. And so instead of taking the inverse cosine or arc cosine of the decimal, I want you to keep it as exact as possible and really plug in the arc cosine of 32, doing that to both sides. Go ahead and use what we talked about on Friday to again confirm the angle. If you have questions, ask up here. From the calculator, then, we do confirm that theta does equal 38.62 degrees. Then the last angle or problem shows a reference to sine. Looking at the reference angle, you're given the opposite side, you're given the hypotenuse, and so the trig function that deals with opposite over hypotenuse is so. And so plugging in what you know, you'll similarly take the arc sine of both sides, which is shown in this next step. Although again, I would hope you'd plug in the fraction to keep it as accurate as possible, and you will get that theta is about 40.32 degrees. Looking at the last examples worked out for you, you're solving for missing sides now in a right triangle. And so we're given 38 degrees as our reference angle here. And so in reference to the 38 degrees, x is going to be the opposite side, and 12 is going to be the adjacent side, as it's not the hypotenuse. And so the trig ratio of tangent compares opposite to adjacent. This time we can plug in 38 for our tangent, and then our opposite is unknown, over 12 is the adjacent. And so this is algebra. Tangent of 38 is a number, it's like 3. So if I wanted to solve this equation and isolate x, I would multiply both sides by 12, and then I would get 12 times the tangent of 38. And so I expect you to skip the next step and just plug it into your calculator. Do 12 times tangent of 38 to be as exact as possible in our approximation, and you should get about 9.38 centimeters. Looking at the second example, we have 16 as the reference angle. Looking at 16 as the reference angle, we have the side opposite, and then we have the hypotenuse. And so the trig function that looks at opposite over hypotenuse is sine. And plugging in what we know, we get the sine of 16 degrees equals 8 over x. This one is a little bit more challenging to think about. If it helps, maybe think of sine of 16 as like 2. And if we had 2 here, I would hope that you would solve the equation by multiplying both sides by x. And so we get x times the sine of 16 equals 8. And then to isolate x, you would ultimately have to divide by the sine of 16, which is how they have 8 divided by sine of 16 in their work. And again, don't even write the decimal equivalent. Plug that into your calculator and be as exact as possible in getting your value for the side, about 29.02 centimeters. Looking at the last example, very similar. We have 55 as the reference angle, and so 18 is going to be the hypotenuse. X is going to be the adjacent side, so that's a cosine trig function, and we plug in cosine of 55 degrees equals the adjacent x over the hypotenuse. If we needed to solve this equation, we would multiply both sides by 18. Again, forgetting that decimal equivalent, and you would get about 10.32 centimeters. I want you to go ahead and try some of these examples out on your own. I'll talk through a couple of them, but ultimately leave you the work to ponder, and then ask that you work on the 6.1 worksheet. Looking at the first example, I have 26 as my reference angle. In reference to 26, x is my adjacent side, and 15 is my hypotenuse, so that's going to be cosine ka. So cosine of the given angle, 26 degrees, is equal to the adjacent side x over the hypotenuse. From here, I'd multiply both sides by 15, and you'll plug it into your calculator as 15 times cosine of 26 degrees, or cosine 26 times 15. And you should get that x is approximately, if we round to 2 decimals, 13.48 centimeters. The next one is very similar in approach, so I'm just going to go ahead and show my work. If you use the sine function and you solve correctly, you'd get x is about 9.95 centimeters. Let's go ahead and take a look at the last one as it switches up a little bit. In this one, we're solving for the angle. And so looking at this reference angle, I have the side opposite and I have the side adjacent as it's not the hypotenuse. So that's going to be tangent. And so tangent of an unknown angle equals opposite 4 over adjacent 5. To isolate theta, we're going to take the arctan or the inverse tangent of both sides. So I'm going to write it kind of small here, but I'll get theta equals the arctangent of 4 over 5. On your graphing calculator, you will have to use the second button and the inverse tangent button in order to calculate theta correctly. And if you do this correctly, you get theta is about 38.66 degrees. I'm going to just show my work on these next two as they're similar to previous examples, and then go ahead and talk through the last example. If you solved these first two examples correctly, you got theta on the first one's about 59 degrees rounded up, and the missing side in number 8 is about 3.60 centimeters. And so on the last one, it's nothing terribly new, it's just making sure that we feel comfortable solving an equation that has a trig function along with some algebra. And so in this example, we have the adjacent side to the hypotenuse, that's cosine, and so cosine of 50 degrees equals the adjacent side 8 over x. In this case, I'd multiply both sides by x to eliminate it from the denominator. And then cosine of 50 is a number, so I'm going to put parentheses around it. So if I wanted to now isolate the x completely, I got it out of the denominator and now I want it on its own, I'm going to divide both sides by the cosine of 50. It's a number. And so I will calculate x by getting the answer to 8 divided by the cosine of 50 degrees. And if you solve this correctly, you'll get x is about 12.45 centimeters. At this time, go ahead and continue working on the practice problems in the 6.1 worksheet.